Hello, I'm Richard Roth, Assistant Professor and Extension Nitrogen Science Specialist with Iowa State University Extension, and welcome to Crops TV. In today's presentation, I have two goals. Number one is to give you an introduction to myself as one of the newest members of Iowa State University Extension, and number two is to walk through different fertilizer sources common in the Midwest. So to jump into an introduction of myself, I grew up in a small farm town in central Illinois, just about 15 miles south of Springfield. I started my education at Illinois State University, where I got my bachelor's and master's degrees in crop and soil sciences. I then moved to Purdue University, where I got my PhD in agronomy and spent a year as a postdoc researcher. While there, I focused primarily on conservation cropping systems with a focus on incorporating cereal rye into corn and soybean systems and examining how that impacts nitrogen cycling processes. In 2022, I left Purdue and moved to Georgia, where I was an assistant professor and extension grains and oilseed specialist with the University of Georgia up until this past September, when I moved to Iowa State University, where I'm now an assistant professor and the extension nitrogen science specialist with Iowa State University Extension. In my time between Illinois State University, Purdue, Georgia, and now at Iowa State, I've gained a lot of experience in a lot of different areas that spans from crop production to soil fertility, environmental quality, using different digital ag technologies such as UAVs and satellite imagery. And then also, I have experience with conducting economic analyses. And this to me is really important because it doesn't make any sense for me to make recommendations to you unless it makes sense economically. Now, when I think about the research that I've done in the past, I've focused on a lot of these conservation cropping systems, like I mentioned, that incorporation of cereal rye into those corn and soybean systems, looking at how they impact the crop, soil, air, and water. Also looking at how incorporating these cover crops into these systems impact the risk that we take on as producers, and using those digital agriculture techniques to evaluate how impactful these conservation systems are. I've also worked in just general production and nutrient use efficiency. One of my main goals at the University of Georgia was to revamp the nitrogen recommendation methods in the state to move from a yield goal based method to more of an optimum nitrogen rate method. And I've also worked with some soybean desiccation techniques as well. When I think about future research for my program, I'm really going to head down that nitrogen management pathway. So 4R nitrogen management, in-season sensor-based nitrogen, precision nitrogen management, nitrogen stabilizer products, nitrogen fixing biological products. But I'm also going to work in areas such as sulfur fertilizer use efficiency, and then continue to work in those conservation cropping systems as well. This is where I, as the researcher at the university, am asking you, the viewer, for your input. If you have ideas of areas of research that you would like to see come out of Iowa State University, please feel free to contact me via phone or email and let me know what you're thinking. And also, if you have any interest in on-farm research being conducted in your fields, let me know and we'll see if we can set something up. Okay, so let's jump into it as far as fertilizer sources are concerned. But before we do, remember that crops don't necessarily care where nutrients come from. So it could be the soil, it could come from fertilizer, manure, organic sources, sewage sludge, any of the other sources that are available. It doesn't really matter as long as they're getting the form that they need when they need it. So we're going to jump into this, and the first thing that we'll talk about is nitrogen fertilizer sources. And the first thing that I'm going to do for each of these nutrients that we talk about is give you an idea of what the full nutrient cycle looks like. And I'm doing this for two purposes. One, to illustrate that it's not as simple as just putting the fertilizer in the ground and the crop taking it up. There's many biological processes that can occur in the soil that can lead to losses of these nutrients, the conversion of plant available nutrients to becoming unavailable, And then the second reason that I want to show you this is to highlight what the plant available forms of these nutrients are. So in the case of nitrogen, which you see on the screen here, it would be nitrate, so NO3 minus, and ammonium, NH4 plus. So the first source I'm going to talk about is anhydrous ammonia. This is in the form of NH3, and it has a fertilizer grade of 8200, meaning 82% nitrogen. This fertilizer is applied as a pressurized liquid, which when it enters the soil turns into a gas, which reacts with the water in the soil and converts to ammonium, NH4+, which is the first of those two plant available forms that we just mentioned. It then goes through some more microbially driven processes called nitrification to convert from ammonium to nitrate, which is NO3 minus. NO3 minus is susceptible to loss from the soil because it has a negative charge, and the soil also has a negative charge. So just like two magnets where the negative poles would repel each other, it's basically the same thing with nitrate and the soil, which leads to those leaching losses that we hear about in the news. So when we think about applying anhydrous ammonia, which is typically going to be injected 6 to 8 inches deep in the soil, we want to make sure that we take some things into consideration so that we're using best practices. The first, and especially important with fall applications, is to make sure that the soil temperature is at or below 50 degrees Fahrenheit and on a downward trend. It's not enough to have just one day of soil temperatures at or below 50 degrees Fahrenheit if the soil temperature is going to warm back up to 60, 65 degrees the following week. We want to make sure that we're there and on a downward trend. The next thing that we want to consider is soil moisture. We don't want to apply when it's too wet or too cold, which could lead to the furrow not closing or the furrow smearing, leading to gas losses of that ammonia. And then finally, we want to consider a nitrification inhibitor, which helps block the process of nitrification, converting ammonium to nitrate. And so what this does is it keeps the nitrogen in the positively charged form, allowing it to be more strongly held in the soil, making it less susceptible to losses. Now, using a nitrification inhibitor does not mean it's okay to apply when soil temperatures are above 50 degrees Fahrenheit. And in fact, nitrification inhibitor efficacy is tied to soil temperature. The warmer the soil temperature, the less effective the nitrification inhibitor will be, so the less time that the nitrogen will stay in that stable ammonium form. And then finally, the last thing that I want to point out here on this slide with anhydrous ammonia is that you want to make sure not to apply too close to planting, as this can cause injury on seeds and seedlings. Now, I talked about the importance of soil temperature when it comes to anhydrous ammonia application, and here I just want to highlight a useful resource that you can use to track soil temperatures. This is the Iowa Environmental Mesonet, and each day they put out a map of the estimated county soil temperatures. And here you can see I just highlighted October, November, and December, and you can see the downward trend in the maps. In fact, this October 28th date is really the first day in the state of Iowa where we were at that 50 degrees or below threshold, and then afterwards the temperature continued to trend downwards. So why do we need to wait until 50 degrees Fahrenheit? We kind of already talked about it, but here on the left-hand figure, you can see on the bottom soil temperature, and on the left-hand side, nitrification. And you can see that as temperature increases, nitrification increases, which means that that conversion from ammonium to nitrate will increase as temperature increases. On the right-hand side, you can see, again, another example of how temperature can affect the amount of ammonium remaining in soils. So in the red bars, which were incubated at 60 degrees Fahrenheit, you can see that we have very little ammonium left after about 9 weeks. However, when incubated at 45 degrees Fahrenheit, you can see that we have pretty significant amounts of ammonium remaining in the soil at 18 weeks, and this trend would continue even past this. So now let's talk about nitrification inhibitors and just some examples of how effective they are. On the left-hand side here, the main takeaway is that the light gray bar is where we have anhydrous with an inhibitor, and the black bar is where we have anhydrous without an inhibitor. And what you can see is that the light gray bar is always higher than the black bar, which means that regardless of time after application, even up to 250 days after application, there was greater amounts of ammonium in the soil where we had the inhibitor versus where we did not. On the right-hand side of the screen, you can see different nitrification inhibitors. So the blue is nitropyrin, the red is Instinct, green is DCD, and then at the bottom, we have ammonium thiosulfate and Nutrisphere. So you can see that neither one of those was very effective at preventing nitrification. And the other thing you can see here is that it took about 5 times as much Instinct as nitropyrin to get to that same level at there that you can see at the top right. And then DCD was always less, so it was less effective at reducing nitrification than nitropyrin or Instinct. Okay, so urea. Urea is a dry granular product with a grade of 4600, so 46% nitrogen. When you're using urea, it's really important that it is incorporated into the soil, either with tillage or try to put it out there before you're going to catch a rainfall. Generally, we would say we want to try and catch about at least a 1/4 inch of rain to help wash that into the soil. So when we apply urea, it reacts with water in the soil to convert into ammonia, which then converts into those 2 plant available forms of nitrogen. And so one of the risks with urea is volatilization, so the loss of ammonia gas from the soil. And this is especially risky if you leave the urea on the soil. So if it doesn't get incorporated either with tillage or rainfall, you really risk the loss of that ammonia gas. So here is just an example of how temperature can affect volatilization of urea. And so across the top, we have temperature, and on the left-hand side, we have days after application. And so you can see that as either temperature increases or days after application increase, volatilization increases. Here's another example of how soil pH can affect urea losses through volatilization. And again, on the top, we have increasing pH. On the left, we have increasing days after application. And the same trend as temperature holds. As you increase pH, volatilization increases. And as you increase days after application, volatilization also increases. So when we use urea, we want to make sure that we're taking into account some of the best practices. So number one is we should avoid fall applications at all cost. They lead to excessive losses of nitrogen, and they're also very much less effective than some of our other potential sources, namely anhydrous ammonia for fall application. So we want to focus on spring applications. This can be either pre-plant or in season. It can be banded or broadcast. Just be aware that if you do try to top dress your crops, it can cause some spotting and browning along the leaf edges. And in corn, that's especially important. If it gets into the whorl, you'll generally see some cosmetic injury. Don't apply urea in furrow. It can cause seedling injury. If you want to put it 2x2 banded, that's fine. Just make sure you watch your rate. We also want to consider the use of a nitrogen stabilizer with urea. So previously we talked about a nitrification inhibitor. Now we're going to talk about a urease inhibitor, which helps prevent that conversion of urea to ammonia. This is especially important if you can't incorporate, whether through tillage or with precipitation. It can help keep that urea in a form that's not susceptible to loss. We can also look at the use of slow release or stabilizer impregnated products. And another positive for urea is that it can be blended with other fertilizers such as MAP or DAP to help get nitrogen and phosphorus needs taken care of. So here's a look at urease inhibitor efficacy. So on the bottom of each of these graphs, we have days after application. And then along the left side of each graph, we have ammonia losses. And In the blue circle that I have highlighted on the screen right now, that is our control treatment, so where we put no urea at all. And then here in red is where we have our urease inhibitors. You can see that compared to the blue lines, which are at the top of each screen, that they significantly reduce ammonia losses relative to urea without an inhibitor. Now, on the figure on the right, you'll see a green circle pop up, and this is actually those polymer-coated products that I just mentioned. And so you can see that they are even better at reducing ammonia volatilization from urea than the typical urease inhibitors are. Okay, so the next product that we're going to talk about is urea ammonium nitrate, also known as UAN. You may have heard it called 28 or 32%. UAN is generally made in a 32% solution and then sometimes diluted down to 28%. Urea ammonium nitrate is comprised of 50% urea, 25% ammonium, 25% nitrate. So what that means is that 50% of the nitrogen applied with UAN is immediately plant available, while the other 50%, which is in the urea form, has to go through those microbial processes to convert it into that plant available form. Now, this is good. However, the other thing that we need to take into account is that 25% of that plant available nitrogen is in the form of nitrate. And so we need to be cautious when applying UAN and try to apply it near when the plant needs it to help avoid the losses of that nitrate. So when we talk about application timing, we're pretty flexible when we think of UAN. You can apply it pre-plant, either broadcast or injected. You can apply it at planting as a starter fertilizer. This can be dribbled on the surface. It can be banded on one or both sides of the furrow, or it can be placed in furrow. And then finally, you can apply in season as well, either injecting. You can also, I've seen people dribble it on the surface, and it can also be used as an herbicide carrier. Though if you're doing that, just be careful, use caution. It can cause leaf burn, as you see in the bottom right image there. And then the other thing we want to consider with UAN is, should we use a nitrogen stabilizer? There's been some research on this as far as urease inhibitor versus nitrification inhibitor versus both. And primarily what we see in the literature is that urease inhibitors help prevent the volatilization of the urea within the UAN and help actually improve yields. We don't see much improvement or additive effect from using a nitrification inhibitor with a urease inhibitor, and we also see less of an effect when we use a nitrification inhibitor alone. We'll talk about manure now and how it relates to nitrogen. The main takeaways here are a couple things. Number one is that application timing is important. I think that probably most people who use manure know that. When you think about the fall, you don't want to wait too late into the fall. If the soil freezes, you're not going to be able to incorporate that manure. We also don't want to wait too long, because the longer you wait, the more manure builds up and you don't want to run out of storage room. And we also need to be cautious when we think about spring application, because if we come into a wet spring and we're prevented from getting into the field in a timely manner, we may not be able to get the manure spread when we want to. The other thing that we want to remember about manure is that not all the nitrogen in the manure is going to be available for crop uptake in the first year. So you can see in the table on the right-hand side of the screen here, the average percent nitrogen that's available in the first year for different types of manure, as well as different types of application. So basically, when we think about broadcasting, you might get anywhere from 20 up to 60% for beef or dairy manure, up to 75% from swine manure and poultry. But when we inject beef, dairy, or swine manure, generally we're in that range of 50 to 70% availability in the first year. The other thing is that some of that nitrogen will be available in the second year. So when we think about beef or dairy manure, about 25% of the total nitrogen will be available the second year, swine about 15%, and poultry about 25% as well. So when you're using manure, make sure you have it analyzed, know the total nitrogen, and know what you can rely on, hopefully, in the first year, and then also in the second year. So the next source of nitrogen that we'll talk about is ammonium sulfate. It has a fertilizer grade of 210024S. So it has 21% nitrogen, but it also has 24% sulfur. It is a dry product, and the sulfur in ammonium sulfate is actually in the sulfate form, which we'll talk about in a little bit, but that is the plant available form. And so all of the sulfur in ammonium sulfate is plant available immediately. The other thing with ammonium sulfate is that it has a lower risk for volatilization compared to other nitrogen sources. So even though it is an ammonium-based fertilizer, the risk for volatilization is significantly lower relative to a fertilizer such as urea, unless, of course, you're in a high pH system. That does not necessarily hold true. One of the cautions with ammonium sulfate is that it can be more acidifying than other nitrogen sources. This is on a per pound of product basis, but generally, ammonium sulfate is more expensive than other sources, and so there's less applied, which hopefully helps us avoid some of that acidifying properties. So here, just a quick example. I told you ammonium sulfate has less risk for volatilization. You can see here compared to urea or even urea with NBPT, which is better known as agritane. It's a urease inhibitor. You can see basically, regardless of time after application, ammonium sulfate always had a lower risk of volatilization than urea or urea with an inhibitor. The final product that we'll talk about is ammonium thiosulfate. This has a grade of 120026S, so 12% nitrogen, 26% sulfur. Unlike ammonium sulfate, not all of the sulfur in ammonium thiosulfate is immediately plant available and does need to go through some of those microbial processes to become available. ATS is quite often added into liquid nitrogen solutions so that you can combine it and get both, your full nitrogen needs as well as your sulfur needs. Do not apply ATS in furrow. It can cause pretty significant seedling damage. You also don't want to necessarily apply it as a foliar fertilizer because it can burn the crop pretty significantly. ATS can be used as an herbicide carrier with caution. It's possible that it can cause compatibility issues or even uneven mixing with some herbicides. The final thing is you may hear sometimes that ATS has urease inhibitor or nitrification inhibitor properties. This is true, though all of the research that's been conducted on it shows that you need extremely high rates of ATS, and even then results are relatively inconsistent. So my recommendation is not to rely on ATS to provide urease or nitrification inhibitor characteristics. Instead, use one of the other proven products that's available. The final thing that I'm going to show you as far as nitrogen is concerned is this source and timing information from University of Illinois. What you can see here, or the main takeaway here, is that all of the timings and products performed relatively similar. If you look, you can see the letters on the right-hand side of this table. Basically, to interpret those, what it means is if it has the same letter in that string of letters as any other line or row on this table, it's considered statistically the same. So it performed the same. What I will point out is some of the poorly performing timing and source combinations, and those are UAN dribbled mid-row, either at planting or at V9, and then UAN with agritane broadcast at planting. Those performed relatively worse than the rest. However, they were still comparable. Okay, so that's nitrogen. We'll move on to phosphorus now. As I said, I'm going to show you the nutrient cycle up front. Again, to highlight all of the processes that can occur in the soil as far as, conversion of available to unavailable phosphorus is concerned. What I'll highlight here again is the available forms of phosphorus are H2PO4- and HPO4 2-. Those are better known as orthophosphates. So orthophosphates are the plant available form of phosphorus. So when we think about phosphorus sources, all of these sources that I'm going to show you are soluble in water. There's no difference really in the P availability to crops. However, some of them do contain other nutrients, and so that is something to consider when choosing a phosphorus source, is if you want to get other nutrients from your fertilizer. So the first and most commonly used phosphorus fertilizer in the world is diammonium phosphate, better known as DAP. It has a grade of 1846O, so 18% nitrogen, 46% P2O5. So you get both nitrogen and phosphorus from DAP. The next is monoammonium phosphate, better known as MAP, fertilizer grade 1152O. So again, you get that nitrogen and phosphorus component with MAP. Okay, so other phosphorus sources include triple superphosphate with a fertilizer grade of 0.450. This is an imported product, so sometimes it can be hard to find, but it is becoming more available in the US marketplace. This is an ideal phosphorus source for crops like alfalfa or soybeans or other legumes where you don't necessarily need the nitrogen fertilizer. The next source here on the list is ammonium phosphate. You may also hear this called ammonium polyphosphate. It has a grade of 10.34.0, so again, getting that nitrogen and phosphorus. However, you should know that the phosphorus here is mainly in the polyphosphate form, so not immediately available to the crops. However, once you apply this fertilizer to the soil, it pretty quickly, just in a couple days, converts to orthophosphate. And in fact, there's been quite a bit of research looking at, is there an advantage of applying phosphorus sources that are orthophosphate versus polyphosphate? And they found that there is no real advantage. And so the fact that it is polyphosphate in this 1034O fertilizer is not necessarily something to worry about. The next source is potassium phosphate, so 0.20.20. So in this fertilizer, you get both phosphorus and potassium. And this is generally used within liquid starter fertilizers. And then the final phosphorus product that I'll talk about is called MESZ. So it has a fertilizer grade of 12.40.0, 10S, 1 zinc. So you're getting not only nitrogen and phosphorus, but you're also getting sulfur and zinc as well. This is a dry product. It can be blended. The thing to keep in mind here is that the sulfur in this product is 50% elemental sulfur and 50% sulfate. So what that means is only about 50% of the sulfur in this product is immediately available to the crop. When we think about manure and phosphorus, it's the same message as we had with nitrogen. Not all of it is available in the first year for crop uptake. However, it's generally anywhere from 80 to 100% of it is going to be available. So again, have it analyzed, know how much phosphorus is there and how much you can rely on for crop uptake from that manure. The final thing I'll talk about with phosphorus is the fact that we did just recently update the guidelines for phosphorus testing in the state of Iowa. The classification categories remain the same: very low, low, optimum, high, and very high. However, the thresholds for the categories were changed, and you can find more information on this in the ISU Extension publication PM 1688. Okay, moving on to potassium. Again, here's the potassium cycle. You can see even with potassium, there's a lot of different transformations that can occur in the soil. And the available form of potassium is free K+. So just the potassium ion. So when we think about potassium sources, the most common is potassium chloride or potash. Generally has a fertilizer grade of 0060 to 0062, so 60 to 62% K2O. Many liquid starter fertilizers contain potassium sulfate, which provides both potassium and sulfur within those starters. And then other sources that exist are potassium nitrate, and then potassium carbonate and potassium acetate can be found in low salt starters. And all of these products are soluble in water. They dissolve, and you get that free K plus ion for your crop from them. With manure, it's the same story as nitrogen and phosphorus. Not all of it is going to be available, but a lot of it will be with potassium, anywhere from 90 to 100%, depending on manure source and application type. But again, I stress that you have your manure analyzed. So some other things that have been asked in the past is, should we side dress liquid potassium? And this is some work from Dr. Antonio Mallarino here at ISU Agronomy. And what he's showing here is the response of corn to either broadcast potassium or side dress potassium, or the combination of both. And what I'll point out here is on the figure on the left, if you notice the red bar, that is the response that we got from the addition of the first 45 pounds of K2O per acre broadcast versus 0 broadcast potassium. And you can see that the response that we got from that is greater than the response that we got from having 0 broadcast potassium and then side dressing 45 pounds of K2O per acre. And so what this means is that it's possible that broadcast potassium, giving that potassium time to convert to plant available forms, is more important than side dressing potassium. You can also see that at any rate where we had broadcast potassium, the response to side dress potassium was relatively low. So the final thing that I'll talk about with potassium is, again, we updated, just like with phosphorus, we updated the potassium guidelines for soil testing for the state of Iowa. Again, the categories remained the same, just the thresholds were changed. And if you want more information on that, you can find it in the same extension publication. So the final thing that we'll talk about is sulfur. The sulfur cycle is, again, there's lots of transformations that can occur. In the top left-hand corner there, you'll see a box that says atmospheric deposition. We're going to talk about that in a minute. But the most important thing to take away here is that the plant available form of sulfur is sulfate, so SO4 minus. So when we think about where sulfur comes from, it can come from a lot of different places. Number one is the soil organic matter. So in most soils, over 95% of the sulfur contained within them is held within the soil organic matter. And in general, we would consider soil organic sulfur availability to be about 4 pounds for every 1% of organic matter. Sulfur can also come from atmospheric deposition. In fact, that's where a lot of the United States used to get most of its sulfur, and why we never used to see much sulfur deficiency in our crops. And that came from the burning of coal or diesel fuels. In certain areas, you can also get it from, not here in Iowa, but in certain areas of the country, from volcanic emissions or marine gases. However, this has significantly decreased over time, and I'll show you that here in a second. We can also get sulfur from manure, from fertilizers and byproducts. And then if you are in an area that is irrigated, you can also receive sulfur from irrigation water. The thing that I do want to point out here up front is that you will not always see a crop response to sulfur fertilizer. It's really hard to determine whether you will see a response or not. But the one time where we generally know you will not see a response is if you do have a field that has been where you've had manure applied or has had a history of manure application. You generally will not see a response in those situations. So here's what I'm talking about when I said it's tough to determine whether or not you will have a sulfur response. So this is some work from John Sawyer, who is retired from Iowa State Agronomy. And what we're looking at here is the comparison of the change in yield relative from sulfur application relative to soil sulfur content from a soil test. And you can see that there's really no correlation of sulfur, soil sulfate to change in yield from applied sulfur. And in fact, some other work that just recently came out last year from Purdue University, they make a pretty bold statement that says sulfate S analysis from fall soil samples is not helpful, and we have found that even soil samples taken between planting and side dress time are not helpful in determining whether a field needs sulfur fertilization. So that's a pretty strong statement that tells us we really don't know how to determine if a field needs sulfur or not. And the reason why soil tests aren't necessarily the best way to indicate whether we need sulfur or not is because they don't account for sulfur leaching, and they also don't account for organic sulfur that's going to mineralize from the organic matter. So I talked about sulfate deposition has changed over time. Here you can see on the left a map of the United States from 1985, and on the right, 2022. And what we're showing here is sulfate deposition. And so back in 1985, here in the state of Iowa, we maybe could have relied on approximately 3 to 8 pounds per year per acre of sulfur deposition from that burning of the coal and diesel fuels. However, in 2022, that number is basically zero. And so rather than relying on atmospheric deposition to get our sulfur now, we may need to switch and start using sulfur fertilizers to make up for the sulfur needs of the crop. So sulfur sources, we've already talked about a couple of these, the top two at least, ammonium sulfate and ammonium thiosulfate. Those you get both nitrogen and sulfur. One of the most common sources is gypsum, calcium sulfate. The good thing about gypsum is the sulfur is in the sulfate form. It's plant available immediately. And another form that is often used is elemental sulfur. So it is 90% sulfur. However, you need to be aware that with elemental sulfur, it does have to go through some processes to become plant available. You can see the other sources listed here. The thing that I do want to point out is at the bottom, you can see it says S in MAP, DAP, and TSP. And so there is sulfur in our phosphorus fertilizer sources of MAP, DAP, and triple superphosphate. It is part of the manufacturing process to generate those fertilizers. However, it's not listed in the fertilizer grade, but I'm going to talk about this in a second. The final thing that I want to talk about with sulfur sources is that you will sometimes hear people talk about using sulfur to manipulate soil pH. So if your soil pH is too high, you can use sulfur to lower that pH. However, what I want to point out is that when you cannot use gypsum to change your pH. Gypsum will not affect your soil pH. So if you need to lower your soil pH, whether that be in a row crop field or if in your home garden you want to grow some blueberries and you need to have generate acidic soil for those, you can use elemental sulfur and that will lower your soil pH. If you find yourself in a situation where you do want to lower your soil pH or you need to lower your soil pH, there's plenty of calculators available online to help you generate rates for elemental sulfur to lower pH. So I talked about there's sulfur in our phosphorus sources. So this is some work that just came out this year from Purdue University, where researchers took MAP, DAP, and triple superphosphate samples from retailers across the state of Indiana, sent them to the office of the state chemist for sulfur analysis. And what they found is that our phosphorus sources have approximately 1.5 to 2% sulfur dependent on the source. So to put that in perspective, if you're applying these phosphorus sources at a rate of 75 pounds of P2O5 per acre, you're getting anywhere from 2 to 5 pounds of sulfur with that application as well. Now, we've been doing this for a long time, and we still see responses to sulfur fertilizers in some fields. And so what this tells me is that, yes, we are getting some sulfur from these phosphorus sources, but we may need additional sulfur as well to see those responses. So in Iowa, our recommendations for sulfur are basically apply it when you need it. And as I mentioned up front, it's tough to know when you need it. But if you find yourself in a situation where you know that you need sulfur, our current recommendations are in alfalfa to top dress 20 to 30 pounds of sulfur per acre. And then for corn and soybeans, if you're in fine textured soils, apply 15 pounds of sulfur per acre. And in coarse textured soils, 25 pounds per acre. And if you're in a corn soybean rotation, apply every other year to the corn, and this will be enough for both the corn and the soybean. Now, to identify sulfur deficiency to help decide whether you need to make these applications, there are some tools that you can use. So for alfalfa, we can use sulfur concentrations in the crop. So if your sulfur concentration is less than 0.23% in the top 6 inches of growth at early bud stage, then that would be considered deficient. So you should make that top dress application of sulfur. For corn, we have less defined guidelines. We can utilize the sulfur concentrations in the ear leaves at silking to indicate sulfur deficiency, but we do not currently have a documented critical level to identify whether or not the crop is actually deficient in sulfur. You can also just use general observations from the field. So if you see striping in your crops, consider it as possibly sulfur deficiency, possibly make those applications. And then if you really want to know on your own farm whether or not you would see a response to sulfur, I would recommend utilizing some replicated strip trials with and without sulfur over several years to determine, whether or not you see a response on your farm. And so talking about sulfur response, here is some examples of corn response to sulfur. These fields here are up in northeast Iowa. This is the response of first-year corn following either soybeans or alfalfa. You can see in the soil sulfate we had results ranging from 3 to 13 parts per million. And what they found is that there was a significant response to sulfur application, which was applied as 40 pounds of S as gypsum, regardless of location, regardless of soil sulfate concentration. Now, I said up front, it's tough to know whether or not you'll see a response. You won't always see a response. Here's another example that is from north central Iowa. This is either first-year corn following soybeans, second-year corn, or third-year corn. And what they found here is that first-year corn following soybeans, there was no response to sulfur. However, in the second and third-year corn, there was a significant yield increase when sulfur was applied. So this just kind of highlights how there's no consistent response to sulfur, and so it's important to test on your own farms whether or not you will actually see that response. Okay, so the final thing that I want to share with you is that we do have an Iowa State University Extension soil fertility website where all of the information that I just shared with you can be found, along with many other very useful resources, good images of what crop nutrient deficiencies look like, and also a link to get to different weather and climate resources as well. This is a useful link. Use it if you see fit. With that, thanks for joining us on today's episode of Crops TV. Feel free to reach out to me with any questions you may have.